asynchronous programming in Java using virtual threads. My name is Venkat Subramaniam. We will talk about multi-threading just a little bit. We'll then talk about threads, some of the problems with the threads that we have had over time. We'll talk about a little bit about continuations and coroutines, and then we'll talk about virtual threads and wrap it up. So that's what we're going to be doing here in this session. So let's first of all start with a quick discussion about parallel and concurrent, and then talk a little bit about parallel and asynchronous as well. There's a lot of confusion among a lot of us, me included, in general about what is parallel, what is concurrent, how do they relate to each other. Well, one way to think about it is, as an example, suppose I was to walk around here, and as I'm walking around, I can speak and walk, but imagine that I have an imaginary glass of water. I'm going to take a sip of water, and then of course I'm going to say a few words, and maybe I want to take a sip of water again, and then say a few words. I think we all can agree that I can walk and talk at the same time. That's parallel. I don't have to stop talking to walk. I don't have to stop walking to talk. I can talk and walk at the same time. That's parallel. So two things can progress at the same time. That's really parallelism. And on the other hand, I think we can agree that it's rather at least impolite, if not really dangerous health-wise, for me to keep speaking and drinking water at the same time. That would be really gross. But I can only speak and drink water concurrently. So, of course, I don't have to empty my glass of water and then start saying words. I don't have to empty my words and then start drinking the water. So I may say a few words, I may take a sip, I may say a few words, I may take a sip. But if you take about 15 minutes, I would have really progressed both on speaking and emptying the glass of water, but I'm doing it concurrently, not in parallel. Meaning, if you take a slice of time, either I'm drinking water or I am speaking, but I'm not doing both. But over time, I'm progressing on both of those. So that's basically concurrency. Well, we talk about parallel versus concurrent, but the question is, what about asynchronous? One of the key things you want to really think about when it comes to asynchrony is it's about non-blocking call. So we want to really think about this nature of non-blocking calls, but what does it really mean to be non-blocking? Now, keep in mind, your task may require a response from a service you are making a call to. And obviously, you cannot go off and do things without the data or the response from a service. So it doesn't make any sense to say, I'll just make a call and keep going, I will not be blocking. That doesn't make any sense. So then what does non-blocking really mean? Well, the non-blocking really is about not blocking the thread of execution, so that thread can be available to do other work. That's basically the nature of non-blocking. But let's understand this with a little bit more example, if you will. So if, let's say we imagine a nice restaurant, a good restaurant, and you walk into the restaurant, you take a seat, and the waiter comes around and says, what would you like to drink? And you say, well, what do you have for a nice drink here? And the waiter gives you a list of things to drink. And now you say, I kind of wonder what I'm in mood for drinking. What do you recommend? What's your favorite? And the waiter is telling you what the favorite is, and then you're saying, I'm still not sure what I really want to drink. Why don't you have a seat over here? Let's talk about it. Well, a good waiter most likely would not entertain that, right? Well, because they need to serve other tables. They'll get fired if they sit next to you and chat for 15 minutes. So a good waiter says, why don't you think about it? Think about what you really want to drink. I'll be right back, and goes away to help other tables. And that's essentially the mode of operation. Now imagine the threads to be like the waiters. Now what do threads do in Java traditionally? Now if I were to behave like threads, how would my life be? Let's think about it. Let's say I go to work, and let's all agree the first order of business when you get to work is to get a good cup of coffee, isn't it? So you walk to the coffee machine, and you realize the coffee machine is empty. It's like, how rude, somebody emptied the coffee machine, and you turn on the coffee machine, it's brewing, and just stand there and don't move at all. Just stand and keep staring at the brewing of the coffee. Your colleagues come to you and says, are you okay? Don't answer them, and only move after you get the cup of coffee. I hope you don't do that, right, as much desperately as we need coffee. You turn on the coffee machine, you go to your colleague and say, hey, are you ready to talk about this design? And your colleague says, I need a few minutes to get ready. You say, all right, that's fine, let me know when you're ready. Then you walk over to check your email. That's taking a little bit of time to download. You're looking at this documentation, and if I ask you, what are you doing? You say, I'm waiting for the stupid coffee machine to fill the coffee I much need. I'm waiting for my colleague to get ready for the talk, waiting for the email server to download the email. I'm checking this documentation at the same time. It's you, but you're in 4 different places at the same time. Well, that's basically how we normally behave. But having said that, how do threads actually work in Java? Well, first of all, threads are considered to be lightweight. But the problem is, the word lightweight is very relative. It's kind of like saying a child is lightweight. Well, sure, a child is lightweight, and maybe 2 years later, the child is a little bit more heavier, but that doesn't mean you cannot really lift the child. The child is a little heavier, but it's really relative in speaking, right? So that's what lightweight is. But how many threads can you really create? That may depend on the memory that you have. It may also depend on the number of cores that you have on the system as well. So if you're doing computation-intensive jobs, you may be able to create as many threads as the number of cores on the system. If you create more threads than the number of cores, you're going to be trashing and the performance is going to get really bad, so you're not going to be able to create more threads. What if I'm doing I/O-intensive operations? Well, if you're doing I/O-intensive operations, on the other hand, you probably can go for a little bit more threads. In general, though, you could say number of threads is less than or equal to, and there's a formula you can depend on. And the formula is that the number of threads you can actually create is equal to, you could say, number of cores on the machine divided by, you could say, 1 minus what's called the blocking factor, where the blocking factor is the amount of time a thread is going to be blocked and wait for I/O to be performed. So think about this for a minute. If you have a computation, let's say, in a computation intensive operations, then you are going to be looking at number of threads is less than or equal to number of cores, because the blocking factor in this particular case, as you would imagine, is equal to 0. Because you are computation intensive, you got work to keep churning, so the number of threads is less than or equal to the number of cores. What if I create more threads than that? Well, while threads are busy running, other threads will ask you to get out so they can get on it. So now you're going to be trashing back and forth, and your performance is actually poorer. This reminds me of an experience I had. We had an application that we're trying to parallelize. The sequential execution took nearly 30 minutes to run. The parallel execution took about 5 minutes to run. And here I was proud, patting myself in the back saying, yay, I brought it from 30 minutes to 5 minutes. And my colleague looked at me and said, I want more threads. I said, you don't want more threads. And he said, you give me more threads, I pay you. I'm like, fine, if you want it, you can have it, right? So we throw more threads on it. What took 30 minutes to run sequentially and what took 5 minutes to run parallel now took 90 minutes to execute. And the reason is, of course, it's completely trashing and the performance is really, really bad at this time, so we had to really think about it. On the other hand, if you have an I/O intensive operation, the number of threads, let's ask the question in this case, how many number of threads can you really have in this case? So if the blocking, let's say, blocking factor, let's say in this case is 0.5, meaning it is blocking half the amount of time, then the number of threads you can have is equal to 2 times the number of cores, if you will. On the other hand, if your blocking factor is, let's say, 0.9, then you're going to block for 90% of the time. You can have 10 times the number of cores in such a case. So the idea really is you can have more threads if you're doing I/O operations. So let's think about this for a minute. If you have, let's say, 100 cores, then for a computation intensive operation, you can really do as many as, you can really have as many as 100 threads. If you are doing an I/O operation, you may have 1,000 threads if the threads are sleeping 90% of the time. Now think about that for a minute. If you can only have 1,000 threads, what do you have to do? You got to scale horizontally. You got to deploy this on the Elastic Cloud so you can have more processes to respond to your request. Now, let's rethink about why we are doing all of this. And if you were to put this in simple English, we are saying, if you call a thread, the thread really blocks and doesn't do a good job. And because a thread doesn't do a good job, we're going to create more threads. Now, that unfortunately is not a great design, isn't it? Because if something is not efficient, create more of it is not going to really get us a success. Now we end up wasting a lot of resources. We spend a lot of money on the cloud for really scaling, and of course it costs us a lot more as well. So let's rethink about what we do. But before we do that, let's think about multi-threaded applications just for 1 minute. Every one of us have written a sequential code at some point in our lives, isn't it? So how do you know you're working in a sequential application, you don't have any multi-threading in it? I'll tell you the easiest way to recognize it. When you go to work, people will actually smile at each other. That's the way you know you're working on a sequential application. They are jovial, they go to lunch together, you have a good time. And as this is going on, one day somebody says, we really need to improve the performance, let's bring multi-threading into the application. That's the last day there was joy in the team, right? And now your code turns into a monster in front of you. You're looking at this code and you don't even recognize it. And you are looking at this and saying, once upon a time, this code used to be so easy to read. Now there is lock and there is synchronize and everything is happening. And then what happens? Late into the night, you are debugging this code. And it's not working. It's producing race condition. You're getting very angry. And while you're suffering through this code, you apply for the other job. That's called concurrency, right? So that kind of concurrency is not really good. So we want to really be able to manage this properly. How can we do this? Well, as it turns out, let's look at the example of how many threads can we create. Now imagine, I'm not even going to do much at all other than simply call it thread.sleep in this particular case. So let's see what's going to happen in this particular example. So notice I have a function called doWork, and the doWork function is not doing much at all. All it is doing is a thread.sleep. That's all it is. Now, how expensive should a sleep really be, right? So this thread is going to sleep for about 5 seconds. Then I define a max of 10, not a really big number. And I'm going to loop through the values. I is a 0 through max, less than max. And I'm going to simply call a thread and assign the doWork to it and ask it to start it. Then I will ask it to say done and then wait for the, about 10 seconds and see what's going on. So a very simple piece of code, isn't it? Now when I execute this code, notice it says done, right? So that's a good news, it worked. Now I'm going to go back to this code and say, hey, why don't you give me 100 threads? That's not a big deal, right? So it was able to handle 100 threads, not a problem. Hey, what if I ask it to give me 1,000 threads right now? So you can see in this particular case, if I ask it to run for 1,000 threads, we can see that it says done as well, not a problem. It was able to create 1,000 threads. What if I asked it to create maybe 3,000 threads? That's not unreasonable, right? Why? Because it doesn't do a whole lot, right? So why not ask it to create 3,000 threads? Now I say, create me 5,000 threads, right? Is the tension going up in your blood right now? You're like, oh my gosh, I'm going for a 5,000 thread, what's going to happen? What if I say, give me 8,000 threads right now? And in this case, when I asked it to create 8,000 threads, it was happy. Now let's say, give me about 10,000 threads right now. And let's see what it tells us right now when we ask for, let's say, 10,000 threads. So right now, when I ask you to create 10,000 threads, it is telling us out of memory error. But actually, it's not. It's even worse than that. Because if you really notice, it says, unable to create native threads. It says possibly out of memory. It's not even sure about it, right? So it's really, it's like, gosh, I can't handle this anymore. But if you really think about it, you didn't ask it to do a whole lot, but why can't I really have 10,000 threads? That's a really, useful question to ask. The reason for that is, when you call a thread.sleep, what's happening? I want you to think about two different things right now. You have a task of execution and you have a thread of execution. Right now, the task and the thread of execution are really intertwined with each other. The task says, I'm going to sleep for 10 seconds. And the thread says, that's a great idea, I will sleep with you, right? And they both are sleeping and taking a nice nap. Now, any parent in the room knows this is not going to work, right? Because when the child sleeps is when you get your work done. So in this case, how did the day go? Oh, the child slept, so I got a nap with the child. Well, the kitchen sink is all filled up right now, right? So that's not going to work really well. So when the task is blocked, the thread is blocked as well. What we need to rethink about is, hey, if the task is blocked, I want to detach the thread away from it. And I want to let the thread go do other things. And when the task is ready for execution, I want to assign a thread to it so it can execute. So what if we can make this non-blocking, as in when the task is blocked, I don't want to block the thread, so I can use the thread for other purposes. Now think about this for a minute. If I am not, I don't have to block the thread, I don't need to create as many threads for execution at the underlying level. So let's revisit this problem in a few minutes, and we'll come back and take a look at it to see how we can work with it. So before we dive into it, let's talk about a concept of what is called subroutines and coroutines, and talk about a bit of a data structure. So what is a subroutine? A subroutine is just a function. That's exactly what it is. So you call a function, send it some data, it sends you back a response, and it's pretty stateless. So you call functions, they give you a response, you call again, you get a response, no big deal. We all have written functions, we may call them methods, but those are just subroutines. A coroutine, on the other hand, is a routine which will remember a conversational state. So it's kind of like you and me when we start talking. I don't rant for 15 minutes and then quietly listen to you for another 20 minutes. We are having a conversation. I say, how's it going? You say, hey, I'm doing great. And I said, when did you arrive in town? And you may say, I came in yesterday afternoon. And now we are going back and forth having this conversation. And I might ask you, which airline did you fly? Obviously continuing on the conversation. So in other words, we have two functions, but the entry point is no longer the beginning of the function. You enter the function, but you exit right in the middle, but then you enter right back into that conversation, and then you go back and forth with this function conversation. So that becomes a nice way to have a coroutine. But when you have a coroutine, this is a bit wicked, isn't it? Because if you and I are talking, if I ask you, where did you fly in from, and you tell me where you flew in from, and if I ask, how was the flight, or I can say, how was it, you probably remember the conversation. And how do you know what we are talking about? That's what we do as humans. We have this conversational state. Now, when you go to a function, you respond back, and you go back in, how does that function know what the state is? That is what a continuation is. A continuation is a data structure that remembers the conversational state. So you call a function, you come back from it, you go back, and automatically the state gets restored thanks to continuations. Let's get a peek at it just to experience what this would do. But before I go into it, I think you will agree, continuation is a great idea, but I think nobody in this room, including me, should directly use it. Because if we do, we're going to cause error in the code. It's going to get really complex. So it's an important data structure, but you want that to work in the background, in the hiding, not in front of us as we work with it. But let's think about this a little bit with a little example to just understand it. So I'm going to quickly show an example in Kotlin just to illustrate this point really quickly. So I'm going to go ahead and call a run function right here. And then I'm going to ask it to execute a task 1 here, if you will, and then I'm going to ask it to execute a task 2 as well. But then I will go ahead and print out, let's simply say calling, let's say the tasks, I'm going to say the tasks, and I'm going to simply say that. But then I'm also going to display right now the thread dot, let's say a thread dot current thread, and I'm going to display the thread of information. Similarly, I'm going to say, called the tasks. So you can see I'm calling it and I'm called it, so you can see that part right now. But I want to define the function called task1. Well, the creators of Kotlin are amazing. They not only created a beautiful language, they want to encourage us to think positively and enjoy what we do. So they called it as a fun. So we remember to have fun all the time. So you say fun, basically task 1, and then here you're going to say, for example, you can say print line, we could say entering, let's say task 1. And then of course you can specify the thread of execution. So I'm going to say here is a dollar, let's say thread dot current thread, and I'm going to display that right there. And similarly, let's go ahead and say exiting task 1. Likewise, let's go ahead and say we want to implement a task 2. So entering task 2, exiting task 2. So nothing really exciting so far, isn't it? So when I execute this code, you can see calling the task, entering 1, exiting 1, entering 2, exiting 2, call the task. Hey, this is synchronous execution, nothing really exciting. This is what life is as usual. Well, that is great so far, but I'm going to go ahead and import, let's say, Kotlin X dot, let's say, coroutines dot start, and I'm going to bring in the Kotlin library right now for coroutines. And just to entertain this thought, I'm going to say, in this case, run blocking. So this is simply saying, call a coroutine. This is the parent coroutine. I want this coroutine to run and only exit when the child coroutines are completed. But of course, I haven't created a child coroutine yet, but I want to create it in just a minute. So then what I'm going to do here is to say launch and start the first coroutine and launch and start the second coroutine right here as well. And you can see in this case, it is telling us calling the task, but did you notice it immediately said call the task, which means that's non-blocking, right? So you didn't wait for that to finish execution, you simply went on with it. Then it says entering 1, exiting 1, entering 2, exiting 2. A little bit of a benefit, but not a whole lot yet. But I want to say that these really functions are asynchronous or non-blocking. Suppose this is going to perform an I/O. It's going to access the database, or it's going to go talk to a remote service. Maybe I don't want to hold the thread for that much amount of time. So I'm going to say yield over here, and I'm similarly going to say yield over here as well. So in this case, I'm saying, hey, I'm doing the I/O. Maybe I'll take a little bit of time to run through this. You go off and do other things if you really want to. Now, up to this point, it's really great, but I do have an official complaint to make. And they really designed this so well, and I really wish they had thought a little bit more before naming this function. They did want to convey that this function is something that is non-blocking. They could have called it as non-blocking fun. That would have been awesome, isn't it? Because, I mean, who doesn't want a non-blocking fun? But unfortunately, they called it suspend fun. How terrible that is, right? So basically, in this case, you are saying that this function is suspendable, and you are indicating that right in here. So when you run the code right now, I want you to carefully notice where we are. You are still in the main thread throughout this execution. We are not doing multi-threading right here. You're in main entirely. However, you called the task, and it says you called them. You entered task 1 in main, but notice you didn't exit task 1. You entered task 2 right now, then you exit task 1, then you exited task 2. So literally, if you ask this thread, where are you? It says I'm in 3 places at the same time, not blocking on any one of those, right? Much like I've got the coffee brewing, I've got a colleague who is getting ready, and I'm looking at the mail server, downloading the mail, and looking at this documentation at the same time. So that is really an asynchrony that you notice. Now, of course, what is really wicked and weird here is, if I were to say here, val, something is equal to 7, I'm going to come down here and print out something right there, and when I execute the code, when I finish the task 1, it tells me the value of that something is 7. How in the world does it remember the state that was initialized here, and it quit right here and came back, and yet it remembers the state? You know the answer for that: continuations. So when it comes to continuation, like I said, it's a data structure that we use. Just to enter in this thought for a minute, we are using continuations, but what if we can think about how this actually works? Just to entertain this thought again, if I define a compute function which takes an integer and it returns an integer times 2, let's say, if I were to go to Kotlin, let's say c-jvm and compile the file sample.kts, and I noticed that it created the bytecode called sample.class. So I use java p minus c minus v, all those good stuff, and take a look at the bytecode it generated. And if I look at the compute function, there is no surprise here. Compute is a function that takes an integer and returns an integer, and it's nicely defined as final as well. So no surprises there, right? Just like a Java function, takes an int, returns an int, nothing really exciting. However, if I go back and say operate for now, and then I say suspend right here. So suspend and operate integer, the only difference between these two functions other than the name is the word suspend that appears right here, right? So no difference. I go back and compile the code one more time. I want to take a look at the bytecode right now once again, and let's take a look at what the bytecode tells us right now. And what you notice here is the compute function is exactly the way it was before, no difference. But because we annotated with the suspend, notice what this function looks like. It contains the integer as an argument, but notice that continuation that shows up right there. That's because the function is a non-blocking function. As a result, when you dive back into it, it needs the state. So the compiler has been working very quietly behind the scene to create this for us. So hopefully that gives you an idea what continuations are. So continuations are data structures that are used to keep the state, conversational state between the calls. So when you go back and forth through this coroutine, it remembers the state you left in, so it can restore it back to you and move on. So with that said, what do we have with threading? How do we solve the problem we talked about? So remember this code where we created the thread and it started failing. We'll just put this back to 10 again. It says done, but let's work with that again. So now enters virtual threads. Virtual threads were introduced as part of Java 19, and as you know, today we are in Java 20. But this is a pre-release version, which means don't put this in production yet. So you can play with it, that's a good idea. As an architect, as a team leader, you can prepare for this. You can know where this is going and get ready for it. Just hold your horses, don't get ready to put in production yet. When it becomes a final release, you can put that in production. So not too far from where we are. But this has been in development for more than 10 years. This has been being developed for nearly 15 years at this point. So this has been done quite nicely over time. They called it Project Loom as they were working on it. This was also really called back in time as Fibers. So these are all different names that were given to it. So Project Loom, Fibers, now it's called Virtual Thread. But what are virtual threads? Virtual threads are super lightweight threads. You can ask, why is it called super lightweight threads? Because they checked around and they found the word lightweight was taken already. So they had to come up with something more than lightweight, so they called it super lightweight. So threads are lightweight, but on the other hand, the virtual threads are super lightweight. You could, to give a silly analogy, threads are light like a child, the virtual threads are light like a feather, right? So they're really, really lightweight compared to the other ones. But the beauty of this is the virtual threads are really managed by the JVM and not by the operating system. So when you create the threads, you are not creating, when you create a virtual thread, you are not creating an operating system level thread. You are really creating a JVM level thread. And as a result, these threads, when you execute, don't block the underlying operating system thread. So as a result, they become really non-blocking. So when your task is blocked and waiting, your thread is non-blocking and they can go around and do other things. So having said that, in this case, when a virtual thread blocks, the task will wait, but not the underlying thread. So let's revisit the problem we saw a few minutes ago. What was the problem in this particular code that we saw? when the sleep was blocking, the thread was blocking, isn't it? So when the sleep is blocking, the thread is blocking, what is the consequence of that? We were able to create about 8,000 threads, and beyond that, we had trouble because all the threads are nicely taking a nap, and you are creating one more thread, and you're like, gosh, there's no more space. Everything is filled up with all these threads. I cannot create any more. I need more memory to create it. But then you ask the question, but what were those threads doing? Oh, the threads were really waiting on these tasks. What were the tasks doing? Oh, they were sleeping, right? So that's not a really good way to explain this, but that's what was happening back in time. What can we do in here? Now notice, I'm going to go back to the code exactly as we saw here, and I'm going to make one change right there. So instead of calling the new thread.start, what I'm going to do here is to say a thread.start virtual thread. So I just changed the code. Rather than creating a thread, I'm creating a virtual thread. That's all I did here. And I'm not starting it. Why? Because it starts automatically when you simply call the start at this point. So we created a virtual thread. That's all we did. When I run the code right now, notice it says you're using a preview feature, right, clearly, because this is a preview release that I'm using, and it tells me done to say that I was able to create it. Now let's go back to this code and say, I want to create 100 threads. Did that work? Absolutely. I want to create 1,000 threads. Did that work? And you can see in this case, the 1,000 threads are not a problem as well. I'm going to reduce this really down to maybe really 5 seconds as well. So you can see that it's able to create the threads, not a problem, right? What if I were to ask it to create, let's say, 5,000 threads? So right now, when I ask it to create 5,000 threads, that's not a problem. Remember, it had a trouble about 8,000 threads, isn't it? So let's go ahead and ask it to create 8,000 threads and see what happens. And notice that it had no problem creating 8,000 threads. Well, what if I asked it to create 10,000 threads right now? That's not a problem, right? It was a blink, it finished it. What if I ask it to create 30,000 threads? Notice that was not a problem. What if I asked it to create, I feel like I'm running an auction here, isn't it? Right? So I can keep going. What if I ask it to create 1 million threads? Do you feel the pressure on your shoulder? Right? You're like 1 million threads, and you're like, yeah, I want 1 million threads. And the JVM says, why don't you give me something more challenging? Right? Not a problem. So the question is, how many threads can I create? And the answer is, as many as you like, right? So there is no limits. Yeah, sure, there's eventually a limit, but it's so lightweight, I created 1 million threads, and it had no problem creating it. So what's happening in this case? The point here is, when you ask your task to sleep, the thread is not spending time sleeping. The thread is like, yeah, you can sleep. When you're ready, let me know, we can run. Conceptually, how does this work? Almost everybody in this room, I'm assuming, has written at some point in your life a desktop application or a Windows application or a Swing application. What do you do in these applications? You don't write code in the UI, you shouldn't, to really do the work, right? So you do your task, and you put a message on the queue. And there's an idle task that says, I don't have anything to do. What should I do? I'll pick a task and execute it. And that puts another task on the queue. Oh, I don't have anything to do. Let me pull from the idle task. Take that concept now in your mind. You have all these threads that are running, and the thread says, you take your time to run. When you're done, let me know. When they finish their job, whether it's making an I/O or a come back from a sleep, they can put a little message and say, I'm ready, and now a thread can be assigned for it to execute. So how many threads do you need? It depends on how many things are active at a given time, so you can have more logical threads in your application, but you don't need as many physical threads to run. So this is a lot more scalable, isn't it? As a result, you don't have to create a cluster of machines just for the sake of scaling your application, because you can run more on a single machine. You perform I/O, no problem. They can go perform the I/O. My threads can be busy doing other work that's important and not block and wait on those. That's truly non-blocking. Let's take the time to get a gist of how this non-blocking actually works. And then we'll think about what is the impact of this particular change, how significant it's going to be. So in that regard, let's think about an example to see how this would actually work. So let's say for a minute I have a fetch function. The fetch function takes a file path as an argument right now. And in here, I'm going to say java.nio.file.star. So one of the things they have taken time is meticulously go through every single function, and they have asked the question, should this really be multi-threaded? Should this be non-blocking? And so on. And they have taken the time to evolve those functions. So as a result here, I'm going to put a little try block, a little catch block with an exception, if you will. And then actually, let's not even worry about well, actually, that's a good idea. Let's put an exception handler. And then let's also put a finally block. And then in the finally block, what am I going to do? So here, I'm going to say output entering. And I'm going to say, in this case, a plus index plus. And I'm going to say a plus, let's say a thread, let's say a dot current, let's say a thread. So we can take a look at the thread of execution in the entering. So I'm going to say int index right now, and we will call that function. Similarly, I'm going to say, in this particular case, finally. So I will say finally, and then an index and thread, current thread. Within the catch, I'm not going to do a whole lot within the catch because I don't expect an exception. But nevertheless, let's just, for the sake of looking at it, if I change my mind, let's go ahead and put, in this case, a catch index, and I'm going to print it. But within this, I'm going to say output. So what am I interested in doing right now? Let's do it this way. Let's say a count is equal to, and let's say a files.lines.paths.get, and the file path I'm interested in using, and we will ask for the count, the number of lines that it sees in the file. So clearly, what am I doing? I'm performing an I/O operation, isn't it? So when I perform an I/O operation, you don't want to be blocking and waiting. Because if you're blocking and waiting for the I/O, your thread is simply idling, waiting for something to work, when it could be switching over and doing, other useful work at this time. So what we are going to do here is to then go ahead and print out, let's say as an output, let's output the count value right there. And when we are done with it, let's go ahead and say here is exiting, and we'll print it. Pardon me. So as a result, in this case, I want to know what's the behavior of this code when I come in, perform an I/O, and if I have a catch, if I have a finally, what's going to happen. Let's take a small example and work with it. So max equal to 10, nothing really exciting, even 5 is enough. And let's go ahead and say, and I'll change the number later if I need to, and I'm going to say I equal to 0, I less than max, and I plus plus, and what am I going to do within this? I want to be able to branch off those calls, so let's say int index equal to I, and let's go ahead and say a new thread, and I'm going to call the fetch function and pass the index right there. I apologize, pardon me. So comma, and I want to say the file is sample.java, right? The current file itself, and then let's do a start on it. Very simple code, as you can see in this particular case. So I've just put that on a separate thread of execution, and let's go ahead and just wait for this. So we'll say a thread.sleep here, for about 5 seconds, and then I'm going to just let that run through. So if I were to look at this piece of code, what am I going to notice in this particular execution? We're accessing this file 5 times, and we want to know what it's going to do. So when you look at the output, you can see that entering 0 in thread 0 in main, as you can see. Excuse me. And then you can see that thread 2 in thread 2, They made the life really easy. The index name and the thread numbers are the same. We printed the size, but did you notice that the 2 was exiting with the 2, much like 2 was entering with the 2? And then similarly, finally, if you look at 2 for the finally, that's a thread 2. So that kind of gives us an indication that they were holding hostage, isn't it? So your thread goes in, it's performing the I.O., and your thread is like, let me have a nice break while the I.O. is being performed. Oh, you're back, let's go on now. So the thread was simply attached to the task and blocked. That's a blocking call. That's how threads were actually working. Now, on the other hand, I'm going to take the exact same code, and before I make a change, I want to make one point right now, and I'll come back and revisit this in about 5 minutes. Notice very clearly, I am not touching this code. That's what I want to emphasize, right? I'm not touching that code at all in the top. I have nothing behind the scenes, so I'm just in the bottom of the screen right here. So I'm making change to that one line of code. So I'm going to go to this code and say, hey, go ahead and call thread.start virtual thread, and I'm going to save that away. That's the only change I made, nothing else. So if I look over here, what do you notice now? Notice in this case, the entering 1 with a thread pool worker 2. So keep in mind 1 and 2. And what does 1 look like here? 1 and 1, as you can see, right? And then on the other hand, in the exiting, wherever 1 was exiting, it's a worker 1. On the other hand, if you look at 4, that was worker 5, and 4 was worker 1 right here in exiting, and then finally, it's a worker 1 as well. So what you notice here is the threads were not being held hostage. If you run this code, you can keep bumping up the threads, and you can do more I.O., and you're not going to be having problems with it. So hopefully that gives you an idea what virtual threads do. Virtual threads are not operating system threads. They are JVM threads. So they are very, very inexpensive to create. When a task is blocking, the thread is no longer blocking, and you can switch really quickly. A couple of observations I want to talk about before we call this done. The first one is, where does it really make sense to use virtual threads? Now, as you would imagine, it makes the most sense to use virtual threads if you're performing I.O. operations. But guess what? That's a lot of what we do these days with microservices and web services and so on, so this fits really, really nicely with it. So, but that's great. We have a better performance. We have better resource usage. Is there any other benefit that we get out of it? I think there is something else we need to think about as a very substantial, significant change that has happened as well in our ability to write code. And that is, we need to really think about how these things are going to make the change to the way we write applications and how we work with it. I'll conclude after finishing that, but a quick commercial break before we do that. There is food after this presentation, so I just want you to remind it. I wish I can say that in parallel, but I have to be concurrent saying this. So don't go away. There is a lot of food available, and there is goodies available. So when you finish this talk, please do join the reception afterwards. I was asked you to convey that message to you, so you've been conveyed. So if you don't show up, I get blamed, so you'll show up. Okay, so now let's talk about the last part here. So let's think about the good old Java. So what was the life in good old Java? I can say the structure of imperative style, parallel code was very different from the structure of imperative style, sequential code. We all know this, right? Because you wrote the code sequentially, everything was nice, you put multi-threading into it, it turned into a monster. You cannot even trace back to the code so easily. Forget about reasoning through this code, right? So sequential code was easier to reason, relatively speaking. This one is really, really hard to work with. However, that changed, isn't it? So in Java 8, there were 2 changes that happened. The first is the structure of functional style let's say parallel code is the same as the structure of functional style sequential code, thanks to, whom should we thank for this? That's right, the Streams API, right? The Streams API did that for us. So because of the Stream API, what can you do? You can simply take a collection, dot stream, filter map, reduce, and you want to make it parallel, change the stream to parallel stream, and you are done. So the structure is exactly the same. So you can write it sequential, test it, debug it. Hey, this is really good. Is the performance adequate? Seems like, just leave it like that. Oh, we can really benefit from performance here. Okay, let's try parallel. It's not expensive to change the code because the structure is exactly the same. That was really, really helpful, isn't it? So that's great. But on the other hand, the structure of a functional style, you can say asynchronous code, is the same as the structure of a functional style. Let me try this again. So the structure of, let's say, the structure of the functional style asynchronous code is the same as the structure of a functional style synchronous, let's say synchronous code. Again, thanks to, whom should we thank here? Thank you, completable future. That's correct. So thanks to completable future, right? So you are absolutely correct. Now, this is great so far, but did you notice a little pattern here? If you want to benefit from the same structure, you have to write code in functional style. Don't get me wrong, I love functional style. But at the end of the day, it is a tool. I'm not going to say that's the only way to write code. It's a saying about a person with a hammer, right? A person with a hammer looks at everything as a fly, right? That's dangerous. And especially the flies on somebody's forehead. This can be really dangerous, right? So we have to be careful. Yes, functional style is great. And I love functional style. I promote it, I use it. And every opportunity I get, I try to refactor it, but I don't want to go to the extent of saying that's the only way to do things. What is great about functional style? Functional style, I would say, functional style is great due to reduced accidental complexity, right? So it's great due to reduced accidental complexity. It is easier to reason, easier to parallelize as well. Those are really good reasons. These are the reasons I prefer functional style. What is functional style not good at, right? So the functional style is not good at dealing with side effects. Functional style is not good at dealing with exceptions as much. So imperative style, you can say, imperative style is really good at dealing with the side effects and, of course, the side effects and exceptions. So question is, if my code has a lot of side effects, if my code has to deal with a lot of exceptions, writing the code in functional style becomes a lot more complex. And I look at this code and say, I lost some of the benefits I have of functional style. Readability is not as good, cohesion is not as good, and I leave thinking, I really need something better than what I did, right? So here comes the charm. With the virtual threads, we'll simply call it as Project Loom. What did Project Loom do for us, right? So Project Loom, not a question mark, but a colon, and guess what? The structure of asynchronous, you can say, the structure of asynchronous imperative style code is the same as the structure of imperative style synchronous code. Did you evidence this in the example I showed you? Right? Because I didn't change the top part, I simply sat there and changed the bottom part in the code. I said thread, virtual thread, virtual thread. I can be synchronous, I can be asynchronous, but I'm not changing the code structure at all. And to me, that is an aha moment in my mind, right? And suddenly I'm like, whoa, I can write my code the way I write it sequentially. I can flip a switch here and can be asynchronous and non-blocking. And that is power to the rest of us, isn't it? That's all I have. Hope that was useful. Thank you.